You're welcome to our physics class today. And in physics, we shall be looking at the topic friction and viscosity. So, what is friction about? Friction is a force that acts at the surface of separation of two bodies in contact and tends to oppose the motion of one over the other. Now, what we mean is this: we have a body such as this, and let's call this body A. This body is at rest, and so no friction on this particular body. If you tend to pull this body, now you will realize that this body will not move instantly. Why? Because there tends to be something between the base of this body A and also the floor. Now, it depends on the material in which the surfaces are made of. There is going to be some form of friction that will not permit it to move at first. The force that is not making it move in this direction as fast as you want it moves it in the opposite direction, and that opposite direction here is frictional force. It is basically a force that acts at the surfaces of A and the surface of this ground. It opposes the motion of this one A over G, which is the ground. We have two basic types of friction. We have what we call the static or limiting friction, and number two, we have what we call the dynamic or sliding or kinetic friction. Now we need to understand the concept behind these things. Now when we talk about static friction, now let's take this body as an example. You have a body like this A on a surface G, and you have a force P which is pulling the body, a gradual pulling of A. To know the intensity of the pull, a spring balance may be attached here. So when a spring balance is attached here, you'll be able to detect the quantity of force which is applied to pull this body. You apply the force slowly, you find out that the body may still remain at its position. It will not move immediately. Continue to increase the force, and when you increase it, you get to a particular force in which the body A is about to move. You find out that if you apply a little more force, the body will begin to move. So before that body moves, the maximum frictional force that stopped a stationary body from moving is called the static or limiting friction. We could use Fs to denote static friction. And then we have what we call the dynamic friction. When you hear the word dynamic, it talks about something that is changing, moving, that has some kinetic energy there. So let us take that this body, we've applied some force, which is the P, and the body has started moving. We keep applying the same force on this body, and it began to move uniformly, so it has a uniform motion. There is still a force which prevents the body to move in equal proportion to the force which you are applying to it. That force is called dynamic frictional force. So considering a body like this body A has its own weight, which is W, and weight is equal to mass times gravity. Now to every action, there's an equal and opposite reaction. Now this body has a force that is also making it to be in equilibrium, and that force, we will call it the normal reaction. The normal reaction is the equal and opposite reaction to the weight. So R is equal to W. When we apply some force to this and it begins to move slowly, the frictional force acts on it in the opposite direction, and then the weight to some extent. But imagine when we increase the weight over here. Let's say that we add another weight to this. We will notice that more force will be needed to pull this body to the right direction that it's going to. As it increases, we'll find that the weight which has increased has led to the increase in this, and as this increases, this also increases. As this increases, we'll find that it has an effect on the frictional force. And so this would lead us to saying that when more load is placed on this A, the normal reaction will increase. So does this Fr. Now the Fr here is going to be Fs, which is the static friction, will also increase. And so we'll call it that there's a proportional increase between F and R. Now this proportionality is being replaced by equal to, so F equal to coefficient of static friction times R. And don't forget that R equal to W, that's normal reaction equal to weight, and weight is also equal to mass times gravity. And we are having that F equal to mu equal to coefficient of static friction and R. So we could have it that coefficient of static friction is equal to F over R. And so we look at the laws of friction. The first law says that friction opposes motion. So just as we've seen, as we are pulling this body, there is a friction that is opposing its movement in that direction. Number two is that it is independent of the area of the surfaces in contact, and then it depends on the nature of the surface. So if the surface of this one is rough, we'll find out that we will have so much of frictional force that will be limiting air from moving in this direction. But if we have smooth body, whereby this ground is smooth, likewise the surface of A is smooth. Now if it is completely smooth, we may even have a zero frictional force, that is, whereby there is no force, and any small force that is applied to move it in this direction will lead to the movement of this body over G. And then we have number 4, saying that it is independent of relative velocity between the bodies. So frictional force is independent of that, and also we have that frictional force is proportional to the normal reaction. So which is this: the frictional force is proportional to the normal reaction, and we have this equation. Then we have that the coefficient of static friction equal to frictional force over the normal reaction. Now once we look at viscosity, viscosity is a name that is given to the internal friction which exists between layers of a liquid or gas in motion. If we have a pipe, and in the pipe water as a liquid flows in this pipe, we would realize that there is going to be friction between the surface of this pipe that's around it with the molecules of the water that's moving. Now the friction around the internal surface of this pipe is more than the friction at the middle. There's going to be more limiting force over here than here, and the viscosity between liquids are different. For instance, let's consider glycerol and water. So glycerol is going to have more friction than water. Now let us consider this. Let's take this as a liquid. Now, and in this particular liquid, we drop the ball. The ball has its own mass. So we have it that the ball exerts a weight which is equal to mass times gravity. When you drop the ball into the liquid, you find out that yes, while it was dropping from the air, it was faster. But when it enters into the water, the speed by which it moves will reduce. And why has it reduced? It has reduced as a result of the upward force, upthrust, and it has also reduced as a result of the viscosity. These are the two forces that reduced the movement of the ball. Now, when we consider the upthrust is the liquid that is displaced. So as you drop it inside, there's an amount of volume of liquid that will be displaced due to introduction of this ball into this liquid. And then we have the viscosity, which is the internal friction between the surface of this ball and the surrounding molecules of the liquid that is there. So we have it that now for this body to continue to move downwards, the weight, which is mg, would have been able to overcome these two forces, which is u plus v, before the body can continue to accelerate. Mind you, while the body was outside falling, it had its complete mass times gravity. But when it entered into the water, the gravity would reduce, and then it will reduce into the acceleration which it will have, and the acceleration is reduced due to all this. And so the body will continue to accelerate depending on the liquid that we are talking about. It may continue to accelerate, or it may reduce acceleration and begin to move uniformly. Now when we say that it accelerates, that means that it continues to fall faster, but after some time to not have that acceleration again, and then it will be falling at a constant velocity, which is uniform speed. Now the uniform speed by which it now begins to move is known as the terminal velocity. So the terminal velocity is as a result of the fact that the ball which was falling inside this liquid is no longer accelerating. And so we'll have it that the v is proportional to the speed. So where this v represents the viscous force, and then we have this V as the speed. So we have it that V is equal to K small v, where this K is a constant. Now at that point, we will realize that since it is no longer accelerating, that is, acceleration has turned to 0, we have it that this particular equation will become 0 equal to mg minus u plus v at this particular point. Number 1. A body of mass 5 kg is placed on a horizontal plane. It is found that a force of 10 Newton applied horizontally to the body is just about to move it. Calculate the coefficient of starting friction between the body and the plane. So we have it like this, that we have an horizontal plane and we have a body which was placed on it. Call it A. It is found that a force of 10 Newton. So we have a force which pulls it, which is 10 Newton, applied horizontally to the body so that it is just about to move. Now that means at that point, what we have there is the static friction. So we have the static friction over here, meaning that this 10 Newton is what is needed to overcome this maximum frictional force. And so we have it that this particular pull, which is the 10 Newton, is equal to the static frictional force. So we take our F to be 10 Newton, and we're told that the body has a mass of 5 kg. So we have it that our weight equal to, that's mass times acceleration due to gravity, mg. M is 5 times 10, that gives us 50. We're told to find the coefficient of static friction. So in this case, we have it that coefficient of static friction equal to F over the normal reaction. So we have a weight here and we have a normal reaction here, and we have that the weight is equal to the normal reaction. And so the coefficient of static friction, where our F, that's the static frictional force, is 10, and then the normal reaction over here is 50, and so we have 0.2 as the answer. Take note that coefficient of static friction does not have a unit. Why? Because the unit of friction here is Newton, the unit of the normal reaction here is Newton, and so they cancel out. So we have this as our final answer. Alright, so let's look at the next question. It says a body of mass 40 kg is given an acceleration of 10 meters per second squared on horizontal ground, for which the coefficient of friction is 0.5. Calculate the force required to accelerate the body, taking g to be equal to 10 meters per second squared. We have a body which is on the ground of mass 40 kg and is given an acceleration so that it will move from one place to the other. So we're having the acceleration to be 10 meters per second squared, and then the coefficient of friction here is 0.5. We have to calculate the force that's required to accelerate the body. Now what this means is that initially the body is at rest, all right, and then it has a normal reaction which is equal and opposite to the weight, which is 400 Newton. That is 40 times 10, that's 400 Newton. So we have our normal reaction, and now we had an acceleration that was given to it. That acceleration, now we're now asked to calculate the force that will be applied to this particular body such that it will overcome the friction. Here is the force acting in this direction, and here is the force acting in the opposite direction. Now what we are now saying is that the force that will be applied to this body will be sufficient to overcome the frictional force and would make this body to be able to move at an acceleration of 10 meters per second squared. This force, let's call it P, will be more than the static friction that is having here. Hence, the force, we'll call it that, which is P, will be greater than this static friction force, and it will produce movement such as we have as MA, whereby this acceleration is the acceleration which we are given. What we are saying in a nutshell is that yes, we have a static frictional force which is limiting this body from moving, but we need force that will overcome this frictional force, and then we'll keep this body moving with an acceleration of 10 meters per second squared. Here is the force which we are looking for, and then we have this, that's the static friction. Now how do we get this? We have the formula which says that frictional force, the static frictional force, equal to coefficient of friction multiplied by the normal reaction. Here we have this to be 0.5 multiplied by the normal reaction, which is equal and opposite to the weight, and this is 40 times 10. It's times 10 because now the mass is 40 kilogram, so the weight is 40 times 10, and that is 400 newton. So the weight is 400 newton, therefore the R is also 400. 0.5 times 400 gives us 200 newton. Alright, so we have P minus 200 newton equal to mass of the body is 40 times the acceleration that we want it to have, which is 10 meters per second squared. So we have, making P the subject of formula, 40 times 10, that is 400, and then 200 comes over here to become plus 200, and so we are left with 600 newton. Here is the force which is required to move the body to overcome the static frictional force and to have an acceleration of 10 meters per second squared. Let's go to this third question, which is quite interesting. It says a body of mass 4 kilogram is on the point of slipping down a plane which is inclined at 30 degrees to the horizontal. What force parallel to the plane will just move it up the plane? Here is a diagrammatic representation of the question. Now in this question, we have a body which is on an inclined plane, and this inclined plane is tilted to have an angle of 30 degrees from the question. Now this inclined plane is placed like this, and then we have the mass on it. Now the mass, this body has a weight and it has a normal reaction. The normal reaction is perpendicular to this straight line. So when we say it is perpendicular to it, that means it goes in this direction. Okay, so this is the normal reaction, that is opposite to it. Now first, we need to be able to resolve our forces. How do we resolve our forces? We need to realize that this is the actual opposite direction of the normal reaction, and so we can resolve it such that this goes in this direction, that is this particular blue line is parallel to this black line. This 30 degree here is equivalent to this 30 degree here, because as this plane was raised by 30 degree, the angle here also will be 30 degree. And so for us to resolve these forces, we could resolve it as this. Now this R here is equal and opposite to this. Because it is equal and opposite to it, so we can resolve it and say that R is equal to this particular force which is here, and this force will be resolved using W, taking this as our opposite and this as the adjacent. We have this as what? The opposite. This particular force here is going to take R equal to W cos 30 degree. So we have succeeded in resolving this normal reaction in this particular direction. Whatever R is here is also equal to this. So if we know what our weight is and we know this 30 degree, we can get this. Likewise, we can resolve. Now let's say that there is a frictional force that is acting in any direction. The frictional force may be stopping the body from coming down. So when the frictional force is stopping it from coming down, that means to come in this direction. So we could resolve this frictional force also in this direction, because as it is, frictional force is going in this direction, that means there's a force acting in the opposite direction. So resolving the frictional force here, so the frictional force or the pull. Now why do I call it pull? It will be a force that is pulling it in this direction. So the frictional force or the pull, when it is resolved in this direction, it will become W sine 30 degree. I would suggest you visit our video on resolving forces, and then you will understand how to resolve forces of such nature. Back to our question. The coefficient of static friction is equal to tan 30 degree. That is, depending on the angle you are giving here. So if the angle you're giving here is 60 degree, the coefficient of static friction will be equal to tan 60 degree. And this particular conclusion was derived from this equation. You know, when you have that coefficient of static friction is equal to F over R, where F is your friction. So when you make W sin theta over W cos theta, you end up having that sin theta divided by cos theta. That will give you your tan theta. So that's how it was derived. So back to our question. We're told that this body of mass 4 kg is on the point of slipping down a plane which is inclined at 30 degrees to the horizontal. So what force parallel to the plane will just move it up? That means we are looking for a force which we call a P, that is a pull, that will move it up. That means as we are pulling it up, there will be a form of friction that will want to prevent this body from being pulled up due to the surface. So we have a frictional force. So we have a frictional force that will be moving. So we have a frictional force at the surface here that will not want it to go up, and that force will be acting in this direction, that is downwards. Now a force that will pull it up will be able to overcome the frictional force, number one, and it will be able to make it move. That means it would have a particular acceleration. So we are going to make use of our ability to resolve these forces. To solve this question, first, let us resolve our forces. What are the forces we are resolving? Number one, we want to resolve this static friction force, which is F of S. Now it is in this direction, and we have it that F of S is also equal to R. This our R here is normal reaction which goes up, and it is equal and opposite to this. So we want to get this particular force, this particular one, and when we are to get it, it is equal to W cos theta. This coefficient of static friction is here, while this R is equal to W cos theta when we resolve it in the opposite direction. Then we are going to resolve a force that will be pulling it up, not necessarily this one. Let's call that force just F. Now that force is in this direction, and this is the equal and opposite force. This is its opposite force which acts in this direction. So that is equal to W sin theta. We're told to calculate the force parallel to the plane that will just move it up. That force will be able to overcome the friction and will be a little bit more such that it will be able to move it up. That force equal to Fs plus, we'll call it F. Alright? Now, Fs here is equal to this. That's coefficient of friction W cos theta plus this F, which is W sin theta. So W sin theta. We have W which is common here. So we have W into brackets cos theta plus sin theta. Now W here is written as mg. So our mass is given as 4 kg times the m times g, which is 10. Then the coefficient of friction we're not given in the question, but we can easily calculate it from our idea of mu equal to tan theta. So tan, our theta here is 30, and tan 30 gives us 1 over root 3. So we'll have our 1 over root 3 here. Then cos theta, where our thetas are 30 degrees. Alright, so cos 30 is root 3 over 2. Then sin 30 is 1 over 2. So 4 times 10 gives us 40 into brackets. Root 3 cancels root 3. We are left with 1 over 2. That's 1, then 2, plus 1 over 2. So we have 40 into brackets. 1 over 2 plus 1 over 2, that's 1. 40 times 1 is 40 Newton. So here is the force, which is enough to just move this body so that it will not slip down. Alright, let's take this next question. It says, a body of mass 2 kg is placed on a rough inclined plane whose angle of inclination is 30 degrees. Find the resultant force acting down the slope and the acceleration if a frictional force of 5 Newton acts between the body and the inclined plane. So we have a body that has mass of 2 kilograms placed on a rough inclined plane whose angle of inclination is 30 degrees. Find the resultant force acting down the slope. Alright, so we have a force that is acting here that is supposed to make the body move downwards, acting down the slope, and the acceleration if a frictional force of 5 Newton acts between. So there's a frictional force that is acting in the opposite direction, and that frictional force is 5 Newton. So that is acting between the body and the inclined plane. Now in this question, we have to calculate the P, that's the force that's acting downwards. It will be necessary for us to have our normal reaction here. We were told that this is 30 degrees, hence this place is 30 degrees. The force acting down here is P. Now for us to get the P, we can get it by making use of this 2 kilograms, and then it is resolved, this P is resolved in this direction. So we have it as W sine 30 degrees. So our W is 2 times 10. That means mass times gravity, then times sine 30. 2 times 10 gives 20. Sine 30 is 1 over 2. So we have 10 Newton. That is the force in this direction. Now the resultant force will be 10 minus 5. It's 10 minus 5 because this force is pulling it down, while this 5 Newton is the frictional force that is stopping you from going. And so the resultant is that this is higher than this. So the body will eventually slide down with a force of 5 Newton. In the second part, we're asked to calculate the acceleration if a frictional force of 5 Newton acts between the body. So we know that the force, which is P, equal to mass times acceleration. Here the force is what? 5 Newton. And the mass of the body which is moving is 2 times the acceleration by which it will be moving. So A equal to 5 divided by 2, and that's 2.5 meter per second square. So that is the acceleration. So in this next question, we're told that the limiting frictional force on a body of mass 4 kilograms resting on an inclined plane is 20 Newton. The angle of inclination theta of the plane is dash. We are looking for theta. What we could easily do is to resolve the forces that we have. We can resolve this frictional force which is acting upwards. We could resolve it in the opposite direction. And when we resolve it in the opposite direction, now it's going in this direction, and then we resolve it in this direction. So this is its equal and opposite, and here is the theta we are looking for. So we are saying that this frictional force here is equal to W sine theta, and our FR here is 20 Newton, and our W here is 40 times 10. That's 40, then sine theta. So making sine theta the subject of this equation, we have 20 over 40. So we are left with sine theta equal to 0.5. So theta equal to arc of sine 0.5, and that leaves us with 30 degrees. So in this question, the angle of inclination is 30 degrees. Here's another question. If an object just begins to slide on a surface inclined at 30 degrees to the horizontal, the coefficient of friction is dash. The body just starts to slide, meaning that the coefficient of static friction equal to F over R. It has just started sliding, so this is the formula we apply. But we are not given any information such as F, the static friction force. We are not given the normal reaction. But we also know that tan theta equal to what? The coefficient of static friction. And so theta is what we're given, tan 30 degrees equal to this. So just go straight forward and find tan 30, which is 1 over root 3. And in decimal becomes 0.58. So this is the coefficient of static friction. Since an object of mass 20 kg slides down an inclined plane at an angle of 30 degrees to the horizontal, the coefficient of static friction is dash. We can make use of the formula, the coefficient of static friction equal to tan theta. That's what we are asked to look for this body. We are looking for the coefficient of static friction equal to tan theta, that is 30, and our tan 30 is equal to 0.577. So that is the coefficient of static friction in this question. So taking a look at this next question, it says a load is pulled at a uniform speed along horizontal floor by a rope at 45 degrees to the floor. If the force in the rope is 1500 Newton, what is the frictional force on the load? So we have a load, which is this. Now it is pulled at a uniform speed at 45 degrees to the floor. If the force in the rope, so that's the force in the rope, is equal to 1500 Newton, what is the frictional force on the load? So we have a frictional force that is opposing the movement. So what we will do is as simple as resolving this 1500 Newton in an horizontal direction. And when we resolve it, we have it that it becomes, this is our x, equal to P cos 45 degree. The P is 1500 times cos 45 degree. So we have 1500 cos 45 degrees is 1 over root 2. So we have 1500 over root 2. We can rationalize this equation. You can check our mathematics video on SOD. You will learn to rationalize this. And so 1500 divided by root 2. So we have 1061 Newton as this x, that is this 1500 resolved in the horizontal direction, and that is the opposite to the frictional force. So we'll have this as our final answer. The coefficient of friction between two perfectly smooth surfaces is what? Is 0. Is 0 because there is no friction. The surfaces are smooth, so there's nothing that is opposing the movement of one body over the other. Next question. A 100 kilogram box is pushed along a road with a force of 500 Newton. If the box moves with a uniform velocity, the coefficient of friction between the box and the road is what? Here we have a box which is being pushed. So we have a push. As it is being pushed, there will be a frictional force acting in its opposite direction. We are told that the mass of the box is 100 kilogram and the force is 500 Newton. It is moving with a uniform velocity. So the coefficient of friction between the box and the road is what? Now as far as the box is moving, so we have coefficient of static friction equal to F over R, where F here is the frictional force. So we'll take it that the frictional, the fact that it has started moving is equal and opposite to the friction. And then we have that our normal reaction, which acts opposite, that is our R, okay, is the mass times the gravity. The mass here is 100 and the gravity is 10, so we have 1000. And so we end up having the frictional force to be 500 because it is opposite to the P, to the actual force, over our R, which is 1000. So we'll end up having 1 over 2. The coefficient of static friction is 0.5, that is 1 divided by 2. That is the answer. In this diagram, the coefficient of static friction is 0.5. If the tension in the string is T, the acceleration of the system in motion is dash. Here we have a body of mass 6 kg is being pulled down by this particular mass, and we have a mass of 3 kg down here. Now this mass is going to limit the quick movement of this 6 kg, but it is not only this mass that is here that will limit its movement downwards, but also the surface which is rough, meaning that for this body to be able to move, we will consider the mass up here, which is limiting it, and also the rough surface. And so we'll take it that for there to be a movement, this particular body, so let's call it that the weight of the 6 gram must be able to overcome the addition of this weight and this frictional force before we can derive its acceleration. So let's call this T. For it to be able to move, this particular weight must outweigh these two impediments. For us to get that done, yes, we can calculate this first one. The weight of this is the mass times 10 minus the weight of the 3 kilogram is 3 times 10, because as it is here, the mass is 3 kilogram and then it has a weight of 3 times 10, that's 30, plus the frictional force. In the question, we're told that it has a coefficient of static friction of 0.5. Now with this information, we can derive the frictional force. The frictional force equal to mu r. The mu is 0.5 and then the r is the normal reaction, because for it to move, it has to be limited by this rough surface, and our r over here is 3 times 10. So that's 0.5 multiplied by 30. We are left with what? 15 Newton. So 15 Newton is our Fs. So we have it as 15 equal to T. So 60 minus 30 plus 15 equal to T. So we have 60 minus 30 plus 15, that's 45, equal to T. So T, the tension in this wire, the tension is 15 Newton. But that is not the final answer, because what we are asked to find is what? Is the acceleration. For us to now get the acceleration, we will consider that we have a mass of 6 Newton being slowed down or limited by a mass of 3 kilogram. What is the difference between the masses? So the difference between the masses is 6 minus 3, and we are left with what? 3 kilogram. So if we have a mass of 3 kilogram times an acceleration will give us our tension, which is the T that we got here. The resultant mass is 3 times acceleration equals to our T, which is 15. Hence, it has A equal to 15 divided by 3. And so we have 5 meter per second squared as the acceleration of this body.